Hey guys, today we're gonna be talking about the periodic table of elements. The topics that we're gonna cover today is a little bit of history about the periodic table, and then the groups, the periods, how the atomic radius changes, how the electrons are organized in the subshells, and in general in the energy levels, and why it is like that. What that has to do with the ionization energy, with electronegativity and electroaffinity, and some basic tendencies that are like universal for the periodic table itself. Now, the introduction, like we're going to talk about the history of the periodic table. First, it was devised around 1869 by Dmitry Mendeleev, who is a Russian scientist. Many of his fellow scientists were also noticing that there were a lot of different tendencies. They were repeating themselves in like different elements, and he, Dmitry Mendeleev, thought that maybe he should like organize them so that it would be easier for other scientists, because at that time they had just they didn't have it as easy as we did nowadays, and they had to memorize all the elements that are known at the time, which when you think about it, that is incredibly hard. Well, now we just have the periodic table and everything is really facilitated for us. And as you can see here, I have written that the elements then were organized by their atomic mass, which, not that it's wrong, but it's not really practical. It's not really practical, and nowadays it's standard, the periodic table to be, not nowadays, it has been for a really long time, but the elements to be organized in the periodic table by their by the number of protons in their nucleus, or by the atomic number, which is basically the same thing. And as we all know, the atomic number is written with the letter capital Z. Yes, now we're gonna look at the periodic table of elements based on Mendeleev's periodic law, where he organized them in groups and periods according to their atomic mass. As you can see, it looks similar to how it looks today, but not exactly, because there are less groups. They're not A and B groups. They're just like 8 groups in total. Now these ones that are in the red, pinkish boxes were not yet discovered, so they were not part of the periodic table of elements at that time. You can also see there are the Dobereiner triads, which are in the boxes with the squared pattern. And those elements, basically, this scientist, he thought that they were gonna be reacting. They're gonna have in general similar physical and chemical properties, so they're gonna react in a similar manner with different compounds. They're gonna behave in a similar manner, which he was right, and they did end up in the same group, as you can see. Now, we're gonna talk about the arrangements. Uh, I have written here that they are arranged in 2 big divisions: metals, heavy metals, or transitional metals, and non-metals, which is true, but there are also the metalloids, which are kind of like they're between metals and non-metals. They're like a lot of the chemical properties are changing, especially like in this area here, like into the transitional metals and the non-metals. It's like when you are going up, they're gonna be changing, or they're gonna become less metal or more metal. It's like we're gonna see there are like there is periodicity as you would expect in the periodic table. Now, why are they divided like that? Not in metals, same metals and non-metals, but in groups and periods. Well, they are divided in periods because in each period the elements have the same amount of energy levels which are being filled by electrons. So in the first period there's going to be only one energy level, and we have hydrogen and helium. They're only filled with one energy level, 1s, and that's it. And then the second period, we have lithium, beryllium, borium, carbon, nitrogen, oxygen, fluorium, and and neon, which is I'm sorry, a noble gas, and all those are noble gases, which we're going to talk about them in a bit as well. But basically, they're all filled like only the second, like 1s2 is going to be filled, then there's going to be 2s. Is it going to be 2? Is there going to be a p subshell field? Well, we don't know. We're going to see in a little bit, but it's important that the second energy level is being filled, which is basically the first one also is written as K, the second is L, M, N, and so on. Usually we only get to N because we don't really use the other elements, or they're not really in a lot of questions, we don't see them. But it's good to know that the first four, like K, L, M, N. Then why are they divided in groups? Well, because first of all, they have similar chemical and physical properties, but that is because they have the same number of electrons in the final subshell, in a specific atomic orbital. Now, in the first group, we're going to have only one. In the second group, we're going to have two. Now, here in the B groups, it's a little bit different, because there is a little bit more complicating how the levels are being filled, because you know the law that the levels are being filled according to their energy. So for example, let's say 4s is going to be filled first before 3d, and here a lot of d levels are being filled, so it's a little bit more specific. But we're not going to talk about that in this lesson. Here now we go back to the A groups, which one electron equals to one group is in one A group, 2 electrons to A group, 3A, and so on. And this is how basically the A and the B groups are differentiated. The A groups are the ones that you can are the main ones. You can see the alkali and the alkaline metals, and the semi-metals, the non-metals, and the noble gases also, as well halogens, and in general non-metals. Here they are going to be, actually those ones are metals, but like non-metal, like this square here, those are the ones that are also from the main group. The ones that are not from the main groups, or the B groups, are the transitional metals. Now you can see here the subdivision of elements and their groups. We already talked about first period, second, third, why it is like that. Now you can see in the main group elements, which are A group elements, the S and the P subshells are filled. Now in the alkali and the alkaline metals, the S subshells are being filled. You can see 1s1, 2s1, 3s1, and so on. It's always S1. Only the S subshell is filled. Here we have 2A, or the second group, which 2s2, 3s2, 4s2, 2 always. Then you can see 3 here. We now start filling up the P, because we don't have any more in the S subshell. S subshell can only take 2 electrons. There is only one atomic orbital. And then in the P we have 3. So that is gonna, more electrons can be filled there. We can see that in each group they increase until we get to 8, which is the number of electrons in all noble gases. And this is basically what all the elements would like to be. They would like to get to this number 8 in the final subshell. And that is why some elements would take electrons to get to that, some would give electrons to get to that. In a lot of chemical reactions, elements like oxidation reduction, they're like giving electrons or receiving electrons again to get to that level. They just love being like the noble gases. That's why they're noble. They're noble also, of course, because they don't react with anything. They're just like on their high horse. They don't communicate with any of the other elements. Now we also have the D subshells. The elements that are the D subshells are being filled in. These, as I said already, are the transitional metals or the B groups. And I also explained why, because here we follow the rules about like which level is going to be filled first. Now here we have the F shells, which lanthanides and actinides are part of this elements, which are the inner transitional metals, which almost all of them are radioactive. And here the F subshells are being filled. This is the only elements where the F subshells are being filled. Okay, now you can see again the electronic structure here. I'm going to repeat again. We can see the alkaline transitional metals, inner transitional metals. Those are, I'm sorry, those are metalloids. Here there's just some again metals. Here we have the metals, which those ones are part of as well, halogens and noble gases. And you can see here which is the final subshell, which subshell is being filled, so which group they're gonna be. Also, according to the number of electrons that they have in the final subshell, you can also deduct what their valence is going to be. So if we look here at hydrogen, it's going to be 1. He has 1 electron. All of those are going to be the first valency. And also like what type of ion they can become. Well, if you have only 1 electron, you can only give 1 electron. And you're going to become a positive ion with 1 positive charge. Here it's gonna be 2, but because they're paired, they're gonna have to be broken down, and yeah, that's how basically you can deduct. Here you have the P level, so the P subshell, the S, D, and the F. Then we have electronegativity, electroaffinity, and ionization energy. Now, what is the difference between electroaffinity and electronegativity? Now, electroaffinity, which is not shown here, but I'm gonna show it to you in a bit, is the energy released when an electron binds to an atom or molecule to form an anion. That is what electroaffinity is. So basically, it's a measurement of energy, like ionization energy. And electronegativity, this is basically a measurement of how much an atom or a molecule, more to be like correct, to be more accurate, we'll have to say atom is able to attract shared electrons to itself, which means that if we have a molecule, for example, let me just if we have like water, because this is like the easiest example that I can think of, we're gonna have 1 electron here, 1 electron here, and here we're gonna have 1 2 1 2, and here 1 1, and we can see that it has 6 electrons. It's in group 6a, part of the p elements. Here you can see 6th group because it's the 7th and the 8th, which is the noble gases. Here we have only 1 electron, 1a group. Here is hydrogen. Now basically that's how it would look like if we did it with Lewis formulas. Now one of the electrons is part of is like hydrogen's electron, the other one is the oxygen's, but oxygen has a much higher electronegativity, as you can see here, compared to the hydrogen, which means it's going to be pulling on those electrons. It's going to be like that. It's going to want to become a noble gas, because if it takes all those electrons, it's going to be like that. It's going to be an anion with a double negative charge. But it's going to have 8 electrons in its final subshell, so it's going to be like a noble gas. And the hydrogen, well, it has relatively high electronegativity, but oxygen's is much higher, so it's just gonna pull them. It's not gonna take them, it's not gonna become an anion, but it's gonna be pulling on them, which means that there is gonna be this partial charge, which is not a real charge, but it is there, because there are some electrons, but not as much as we would usually see. So this one is going to have a really big partial negative charge, whereas the hydrogens are going to have a partial positive charge, both of them. And basically we're going to get like a dipole, which is like that. Here's the oxygen, here are the two hydrogens with the partial positive charge. And usually molecules like that have like one element that is really has really high electronegativity, or it's really electronegative, is going to be pulling on those electrons, and we're going to have a molecule which is not going to be electroneutral. Now we're going to go to ionization energy. Which is base ionization energy, which is the energy needed to be exerted, or is used up, or is released when is used up when an electron is being removed from an element, so it can become a cation. Now we can see that the alkali and the alkaline metals, and in general metals, have, I'm sorry, why am I looking here? I should be looking here. Have a really low ionization energy, which means they don't need so much energy to give that electron off. It's easier for them. Like we can see here that lithium, for example, it just has one electron because it's in 1A group. So if it gives it off, then it's gonna have the same configuration as the I think it's supposed to be neon. Yes, I think it's neon, which is noble gas, and it's gonna have 8 electrons, which is perfect in that case. We want that. It wants that. Lithium wants that. It wants to be a noble gas. As I said, everyone wants to be a noble gas when they're reacting or they're becoming something in the periodic table. And for the other elements like noble gases, they cannot. They're stable, they're perfect, they don't want to change. There are also some metals like, for example, mercury, that is also really hard to. It's really hard for them to give off electrons, but they do nonetheless. It's not impossible, but it's hard. Now, as we already said, what affinity is. That is the measurement basically of energy, which is the energy that is used to for an electron to be incorporated in the energy levels of a specific atom. So the atom is going to become an ion in the end. Now you can see that they have a high electroaffinity that is specific for all nonmetals, specifically the uh, halogens. Um, and basically, yeah, well, if they are gonna have high electroaffinity, they're gonna have really high ionization energy as well, and they're also gonna have high electronegativity because they just love electrons. They want to get them, they want to have them near them so they can become noble gases. But the electroaffinity is really low, as well as the electronegativity for all metals. They don't want electrons. They prefer to have less. They just want to be positive. They're positive. They are present, but most of the non-metals are prefer to be negative. Okay, when you look at the atomic table, one might think that when we're going, it's a little bit confusing. Why when we're going down it's increasing, but when we're going to the right, like across the period, it decreases. Okay, it's not so hard actually. Now, down a group, when we're going down a group, the atomic number is going to increase, which means more protons in the nucleus and more electrons in the electron cloud. But here the valence electrons are gonna be further away from the nucleus, and that is because as we're going down, we're going also increasing the energy levels, because all those elements are going to be in different periods, and as we said, each period correlates to a specific energy level. Now when we have more energy levels, we have more subshells, and the valence electrons are going to be farther away from uh, the nucleus, so the nuclear charge is not going to be pulling on the electron cloud, on the final levels of the energy levels of the electron cloud. Whereas when we're going from left to right, here we see that there is a decrease in the atomic radius. That is why, because the effective nuclear charge increases when we go across a period, but the electron shielding remains constant. So here we saw that energy levels increase, and that's why they're not being pulled so much by the nucleus. But here there is no such thing. There is just an increase in the nuclear charge. Yes, there is an increase in the electrons in the electron cloud as well, so the atom is electroneutral, but the charge is powerful and it's pulling on the valence valence electrons, and they're really coming closer. The whole electron cloud gets closer to the nucleus, which results in a smaller atomic radius. Here we can see that how the atomic radius decreases. Here in aluminum and magnesium it's a little bit like aluminum is actually higher, because in sodium and magnesium we have S only, or atomic orbitals that are S subshell, I'm sorry, that are being filled, but here we get the P, so it's gonna be a little bit bigger. And then there is a constant decrease, because we already said the effective nuclear charge is pulling on the electron cloud and the valence electrons with greater force. Now the ions, we can see if we give off the electron, the atomic radius is gonna decrease accordingly, and if we receive an electron, the atomic radius is gonna increase, because we have now we're gonna be filling up more subshells, maybe even another energy level, which is gonna increase the atomic radius. And now we're gonna have a brief summary before we solve some exercises. We're gonna start with electronegativity, which is the tendency of an atom which is participating in a covalent bond to attract the bonding electrons. As we saw before, the example with the water and how the oxygen is pulling the bonding electrons, the electronegativity is from left to right is increasing. So from left to right is increasing, and from bottom to top is increasing as well. And here the most electronegative element would be fluorine. For the noble gases, we cannot distinguish any electronegativity and like define it as anything, because they're very stable. They don't like reacting, as we already stated, and they cannot give off or accept or take electrons. No, they're just chilling. They're not participating in anything. Then now we can talk about ionization energy. Ionization energy can be defined as the minimum amount of energy which is used to remove one electron, and it's going to be the lowest on this side of the periodic table, and at the bottom as well. So basically here, where is the most metallic element, the ionization energy is going to be the lowest. And why is it impossible for elements here, or especially noble gases, to give off of any electrons? It's because they have a stable configuration, and if it is if we remove one, that will be disturbed. Now it's going to be increasing from left to right, because here we have the more metallic character. More metallic character equals less ionization energy. and here we have the more non-metallic character, so ionization energy is going to be higher. Same goes from top to bottom, because as we talked, metallic character becomes more prominent as we go down the periodic table, and non-metallic increases as we go up the periodic table. So ionization energy is going to follow that. Electron affinity, we have not talked about it yet, as we already stated before, is defined as the amount of energy released when an electron is attached to a neutral atom or molecule in the gas state, which would result in the formation of an anion or a negatively charged ion. Electron affinity is going to be the highest, of course, with elements that are non-metals, because we know that they have usually, like, the outer electron shells, subshells to be exact, are closer to the nucleus, so the effective nuclear charge is going to be pulling more, which will result it's going to be easier for them to get an electron. Furthermore, they're going to be following the rule about the noble gases. They would like to get more electrons so they can become have the same stable configuration as them. And as you can see, it follows the same trends as ionization energy and electronegativity, nothing new. And now, last but not least, we're going to talk about the atomic radius, which has the opposite trend in the periodic table, since as we go down a group, there is going to be one extra electron shell, because we said, like, the energy levels are going to be increasing, more electron shells and subshells, and as a result the atomic radius increases. But when we go to the left, we talked about the effective nuclear charge and how it's affecting the electron subshells and energy levels in general, and how it's pulling on the electron cloud. And now we're gonna try to solve some exercises, and if you have any problems with them, you can always just go over the lesson again, and I'm pretty sure then everything's gonna become clearer. Now, arrange the following from lowest to highest electron affinity. Now we have rubidium, arsenic, chlorium, and gallium. Now, electron affinity, we already talked about what electron affinity is, which is basically the energy which is released when to a neutral atom an electron is being attached to a neutral atom, and it becomes a negatively charged ion or an anion. Now, we talked about how the electron affinity is going to be increasing from left to right, because electron affinity is highest in the nonmetals area, so basically here it's going to be highest. Then we can see, just by looking at where those elements are located, we can kind of start like understanding what type of physical and chemical properties they're gonna have. So we have rubidium, which is here in the alkali metals. It's pretty down the periodic table, but when we say that it's in the group of the alkali metals, it's obviously a metal, so the electron affinity is gonna be really low. It's not gonna release a lot of energy. They just don't. Those, like, this atom is not gonna attach to a new electron. Then we go to gallium, which is again kind of like after the semi-metals and before the metalloid semi-metals. The transitional metals. I'm sorry, and the metalloids. Those are the semi-metals, and you're kind of like, okay, it's gonna have higher electron affinity than rubidium, but you can see that they're in the same period. We have gallium and arsenic. Are they gonna have the same electron affinity? Well, no, because as we go to the right, electron affinity is gonna increase. Furthermore, this one, arsenic, is a little bit closer to the chlorium and everything, and towards this part of the table, so it's gonna have a more non-metallic character than this one. So again, this is a clear sign that we have a higher electron affinity. And then we have chlorium, which is a halogenous gas, and above it is fluorine, which is the element that has the highest electron affinity. So we can say that the highest electron affinity of the given elements, the element that's going to have the highest electron affinity is going to be chlorium. And basically now we can just see if, okay, we have this is the lowest, then we have gallium, arsenic, and chlorine. Okay, now let's see if we are correct, and of course we are. Why is that not correct? Well, rubidium, it's the same, that is correct, but then gallium is correct as well, but then arsenic to be have a higher electron affinity than chlorium. No, I'm sorry about that. in no circumstance can that be correct. Then chlorium is going to have the highest electron affinity, as we already said, so this from the beginning you can say that it's wrong. And here we have rubidium. It has, supposedly, according to the answer, it has a higher electron affinity even than arsenic and gallium, which is impossible. They are like metalloids and closer to non-metals, and this is one of this the most metal basically. And now we're gonna solve the second exercise. So as you move from top to bottom on the periodic table, why does electronegativity increase? Okay, now I'm gonna give you some time for you to look at the questions. You can pause the video if you need more time, and just think what we said about electronegativity in general, what it is, why it works like that, and something about the atomic radius that might be like a little bit of a hint that will help you with the answer. And now I'm gonna show you what the right answer is, and that is the first one. It is because electronegativity is the force, not the force, but that is the tendency of an atom in covalent bond to be pulling on the bonding electrons. Now, in order for an atom to have that tendency, they need to have a smaller atomic radius. And why would they have it? And which ones have the smallest atomic radius? Well, the ones that are like more up, because they have only one energy level. So they or like the second one, third one, but like compared to the ones that are below them, they're gonna be farther away from the nucleus. So the effective nuclear charge is not going to be pulling on the electron cloud so much. Even I mean it will for sure, but just not as much as the ones that are like towards the top of the periodic table. So the interaction between the nucleus and the bonding electron decreases, yes, because the outermost electrons get farther and farther away. And this is the final exercise, which consists of those three subpoints, and we're given three elements, A, B, and C. And for all of those three, we have their atomic numbers, their respective atomic numbers, which means that we can write down what is the number of protons in the nucleus and the number of electrons. Now we have 10 here, so 10 protons equals 10 electrons, because as we all know, atoms are electron neutral. Then we have 17 protons and electrons, 19 protons and electrons. Then now we have to write down the electron configuration, yes, and then we're gonna do the next step. But now let's first, okay, we have 10, so we have 10 protons equals 10 electrons. Okay, now we only care about the electrons right now. And now there are a couple ways that you can do it. You can just do it like 1s and then 1 2 and 2s 2 p 6. You have 1 2 4 plus 6 10 and that is a noble gas. Then there is the other way that we can do it. We can do it with the energy levels. Okay, L. Then we write the atomic orbitals, and we just do 1, 2, 1s2, and then we do the other one here and the other one here. It's kind of like crammed a little bit. You're gonna have to excuse me. And here it's gonna be 2s2, so 1, 2 electrons, and then 1, 2, 3, 4, 5, 6. Both of them, they mean the same thing overall, and you can get the general idea how the element that we're looking at, where it's located, what type of character it's gonna have, like what are going to be the physical and chemical properties to some extent, the valency, and things like that. Now, you can use whichever method is more comfortable for you, and in other videos we have already talked about how to do it, why the configuration is like that. Okay, and now here we have the first step, how it's supposed to look like. We have, we have A, which we said that it's a noble gas. Here we have a non-metal, a halogenous element, and here we have a metal. Why? Now, I say it like that because it looks like I'm just like guessing, but I'm not. Here we can see that in the final subshell and in the final energy level in general, we have 8 electrons, which means 8 electrons, the only elements that have them are the noble gases in the final subshell. Then in the other one we have 7, which means it's the 7th group, and halogenous element. And then here we have only 1 electron in the final subshell, a metal, alkali metal. And that exactly is the next step. We have to locate all of those elements in the periodic table. Which period, why are, okay, now let's see why they are in those periods. In second, because we have 2 energy levels. In third, because we have 1, 2, and 3. And fourth period for the C element, 1, 2, 3, 4. And the groups here, we have talked that you can write them both ways, but this one is like easier, I would say, like it's more practical. And then after that, we have to create like a small periodic table, like something makeshift, like, you know, something super simple, and note the trends. So basically we know which period, so we're gonna write second, third, and fourth period, and we're gonna write first, seventh, and eighth group. Pretty straightforward, it's not hard. And then you just have to write the trends. Now we have to do the trends that we have to write down and how they change across those elements are electronegativity, atomic radius, and ionization energy. Now, electronegativity, ionization energy, and electron affinity, we have talked what they are, and we know that the farther to the right we go, they increase, all of them. Electron affinity, because they love more electrons. Ionization energy, because it's incredibly hard for them to give off electron affinity is they release much more energy when they receive an electron. An electron is being attached to a neutral atom. The ionization energy is the energy which would be released if an electron is given off, but it's incredibly hard for all of those elements, especially non-metals. And electronegativity is how much they love electrons, put simply. And then we have also atomic radius, we can just put that way because it's going to be increasing in that way. And we already talked why, about the effective nuclear charge as well as the number of energy levels. And basically now we have to put those elements in order of increasing or decreasing electronegativity, like who has the highest electronegativity in that case. So from highest to lowest. So higher electronegativity has the element P compared to C. Then we have atomic radius. C has higher atomic radius than P, B has higher than A, and ionization energy, the highest ionization energy A has than P, and C is the lowest. And that's what it's supposed to look like. Now we're going to the final slide. We finally did it. We finished this lesson. You can try this book. It's really good and it's gonna help you a lot with your preparation. And I would like to remind you to subscribe, of course, and like, so we know that you appreciate our work and that what we're doing is helpful for you. So we would like also feedback in the comments. If you have any questions, you can also write them in email, write us an email, and we're gonna reply. And I am sure that all of you can do it, and it's not gonna be a problem, especially after the lesson. Everything is pretty straightforward. You just have to be concentrated, and if you need to go over everything again, that's completely fine. Take your time. Nothing happens in an instant, so just keep on working, and we're gonna see each other in the next video.